Okay, a little laser pointer. There we go. Starting a new module in EnMath A, Engineering Math A. Engineering Math A is kind of a collection of a bunch of different math topics useful. This particular module is all about matrices. It's kind of a long module. So here's what this whole module will cover. First, we'll do a bit of a review of matrix definitions and arithmetic. Hopefully you're at least a little familiar with matrices, but still I think everybody ought to go through this review so we use the same terminology, get you up to speed. And then there's a whole bunch of subjects to cover. One thing is using matrices to solve systems of algebraic equations. And that's going to lead to Gaussian elimination. And we want to characterize systems of equations, not just solve them, but how many solutions are we going to get? That kind of thing. And before we get there, we need to talk about matrix rank, talk about matrix determinants and its their properties, inverse of a matrix, and the adjoint matrix. And then lastly, it's kind of a bunch of subjects ultimately dealing with solving systems of differential equations. So we need to cover eigenvalues and eigenvectors, diagonalization, systems of differential equations, and solving those. So that's kind of what we're going to cover. In this particular recording will mostly be the review of matrices. What is a matrix? A rectangular array of numbers. We say it has M as in Mike rows, N as in Nancy columns. So its size is called M by N, rows by columns. We say the JK element matrix is the number in row J and column K. Somewhere over here is the AJK element. Row J, so come down J and over K. Here's some examples of sizes. This one's easy, 3 by 3. This one is 2 by 1. This one is 1 by 3. Here's 3 by 2. That's matrices, definition, and their size. How do you add matrices? First, you can only add matrices of the same size. And you just do it element by element. The JK elements add. So this 7 will add to that 2 to give us a 9 over here. So matrix addition is easy. Subtracting is the same kind of thing. It's commutative and associative, all those good things. Scalar multiplication is also easy. If I put a little scalar in front of the matrix, it means multiply every element in that matrix by that scalar. So if this is A, 2A is going to be 4, 2, 0, 10, etc. Multiply everything by that scalar. Scalar multiplication is also associative. Matrix multiplication. Now here's a little bit more tricky. They have to be compatible size. What does that mean? If I do the product AB, where A is in front, and by the way, the order matters because it's going to turn out it's not commutative. Matrix multiplication is not commutative. So the order matters. If I multiply AB, A must have the same number of columns as B has rows. There's a way to determine the result of the size of the result. Let's say A is M by N, then B must be N by something else. These two sort of inner numbers need to match. And the result will be the outer numbers. In this case, M by P. And I could do that to a whole list of things. Say each one of these, I have their sizes here. See, these inner numbers always have to match. Otherwise, you can't multiply those. And the end result will be M by R. First thing and the last thing. It is associative, but it's not commutative. AB is not equal BA. In fact, BA might not even be possible, even though AB is. They have to be compatible size. How do you do it? Think of multiplying the rows of the front matrix by the columns of the second trailing matrix. So first, let's say I have these two matrices A and B, and I want to multiply A times B. First, is that even compatible? A is 2 by 3. B is 3 by 2. Those inner threes match, and the result is going to be 2 by 2. How do you do that? The top left result in C is going to be this top row times this left column. 3 times 2 is 6, plus 1 times 6 is another 6, plus 5 times 3 are 15. That arithmetic, that element is 27. For the entry down here, it's going to be the bottom row still times that first column. 4 minus 42 plus 12. Whatever that is, but it ends up being minus 26. Arithmetic's not easy here. Let's do some sort of simple things. First, things might not even look like you can multiply. You have to check it out, make sure the sizes match. This guy's, I've got a 1 by 2, and then a 2 by 1. They're compatible, and the result is going to be a 1 by 1 matrix. 3 plus 8 is 11. Here I have what I had 2 by 1 and 1 by 2. So in this case, they're compatible, and I'll get a 2 by 2 matrix. Top left is 1 times 3. Bottom left is 2 times 3. Right, 1 times 4, etc. How about this one? I have a 2 by 2 and a 1 by 2. Uh-oh, the 2 and the 1 don't match. They're not compatible. Some definitions for other matrices. And, well, first, what is a square matrix? It just means same number of columns as rows, or M equals N. So here's a 3 by 3. The main diagonal is a pretty important concept in these guys. That's from top left to bottom right. In this case, the 1, 5, 9. There's the main diagonal. We never even talk about the other diagonal. It's the way we do things, a useless thing. That's what we call the main diagonal, top left to bottom right. And these other terms, triangular and diagonal matrices, these definitions only apply to square matrices. Upper triangular has all zeros below the main diagonal. Below and left, the main diagonal. This guy is upper triangular. Lower triangular has all zeros above the main diagonal. And diagonal means all zeros off the diagonal. So the main diagonal elements themselves are only non-zero elements, if any. But, okay. The transpose of a matrix, you just switch its rows and columns. And its notation is, its notation is this script T. That means the transpose of A. So if A is M by N, its transpose will be N by M. And each element, you just switch, easier to see it than describe it. So this guy's transpose, you just turn it from a row matrix into a column matrix. This guy, let's see, the top row of the transpose will be 1, 2, 3. Second row, 4, 5, 6. Or I could think the first column of the transpose will be this guy's first row, 1, 4. 5, etc. You can just see, you just switch everything around. The main diagonals will stay the same with the transpose. 1, 5, 9 here, 1, 5, 9 there. But everything else gets switched. This 2 will go down here, this 3 will go down here, etc. That's transpose. The zero matrix. You can have, well, the zero matrix is a matrix of all zeros. It could be any size. And if you add the zero matrix to any other matrix, you get the matrix again. So like normal arithmetic, you add the zero matrix to a matrix, you get that matrix. If you subtract a matrix from itself, you get the zero matrix. The identity matrix. It's so special, we give it its own numeral or identity. The capital I means the identity matrix. It's always a square matrix. It's always a diagonal matrix. And every element of the main diagonal is 1. And if you multiply any matrix, either front multiply or post multiply, once it's compatible size, it returns the other matrix. It's called the identity. It's kind of like the number 1 for just scalars. Here's an example. Remember, order matters. So in this case, if this is the A matrix and we pre-multiply it, it's a 2 by 2. Convince yourself, carry out this multiplication, you get the matrix back. I could also post-multiply by an identity matrix, but the size must be compatible. So in this case, if I post-multiply, it's a 3 by 3 identity matrix. Carry out this multiplication, and again, satisfy yourself, you get matrix as a result. A symmetric matrix means its transpose equals itself, or the JK terms are the same as the KJ terms. It's easier to look at it because the upper triangle is the mirror image of the lower triangle. The lower triangle is a mirror image of the upper triangles. 2 there, 2 over there, 6 there. Again, the main diagonals always stay the same regardless. That's what symmetric means. And I'll do one more series of definitions before we get into using these to solve systems of algebraic equations. Echelon forms. First, I'm going to call the pivot of a row of a matrix is the first non-zero entry from the left. So here's a pivot. Here's this row's pivot is this one. This row, its pivot is this one. This row doesn't have a pivot. First non-zero entry from the left. A pivot column is the column of the matrix that contains the pivot point. So this is the pivot column corresponding to this pivot. This is the pivot column corresponding to this pivot. We say a matrix is in row echelon form if it satisfies these 3 conditions. Every pivot is a 1. Each pivot is strictly to the right of all pivots of the rows above it. And any rows of all zeros are down at the bottom. So let's go through some of these and see if they're in row echelon form. This pivot is a 1, this pivot is a 1, no pivots here. That's good. This is the top pivot, so this doesn't apply. This is the pivot here, and yes, it is to the right of every pivot above it. That's good. There are no more pivots, and rows of all zeros are down at the bottom. So yes, this guy is in row echelon form. About this guy. This pivot is a 1. Pivot is a 1. This guy is to the left of this, not strictly to the right. And it means strictly to the right. So even if the 1 were here, it's still not in row echelon form. This guy is not in row echelon form. What about this guy? That pivot is 1. This is actually its own little column. It's not 22 and 14. It's a column of 2 and 1 and another column of 2 and 4. There's a pivot, it's a 1. Here's a pivot, it's a 1. This guy is strictly to the right of that guy. And there are no non-zero rows, but it satisfies all 3 rows. This guy is in row echelon form. Then there is reduced row echelon, which adds one more criteria. It satisfies all these, so it's in row echelon form. It's in reduced row echelon form. Each pivot column is all zeros, except for the pivot itself. Let's look at this guy. It was row echelon form. Here's a pivot column, and it's all zeros, except for that pivot. Here's the other pivot column. Oops, it is not all zeros. So this guy is in row echelon form, but not reduced row echelon. What about this guy below it? Pivot here, 1, pivot here, 1, row of all zeros. This guy is to the right of that guy. It is in row echelon form. 2 pivots. Here's the first pivot column. Zeros other than the pivot. Here's the second pivot column. Zeros other than the pivot. This guy is in reduced row echelon. What about this guy? We said it was in row echelon form. Look at this pivot column. Pivot, this guy is not 0, so this guy is not in reduced row echelon form. What about this guy? Pivot, it's a 1, pivot, it's a 1. To the right of that guy, it's in row echelon form. Has a 0. Another pivot column, that guy's a 0. This is in reduced row echelon form. Okay. Now we'll start using some of these concepts to solve systems of linear algebraic equations. Another recording.